Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving another locus problem with arg or arg. So we have the argument of z plus 2 over z equals pi over 2, and we're going to be solving for z values that satisfy this equation. I'm going to show you something at the end which is really cool, because when we solve this problem with the first method, we're going to see something different. Anyways, let's get started. First method. Since I was given the argument of a quotient, I can actually use the Moivre's formula, right? And what does that say? If you divide two complex numbers, you subtract their arguments. In other words, argument of z divided by w is the same as argument of z minus argument of w. Okay? Now, how do we apply it to our situation? Well, easy. Kind of like the natural log, which is interesting, right? It kind of carries the same property. We can split it up into a difference. So we can write this as argument of z plus 2 minus argument of z is equal to pi over 2. And now what am I going to do with this? There's a couple ways to go about it. But one of the methods that I really like is using trigonometry and the quadrants. I'll show you how that conversion is done. So let's go ahead and add arg z to both sides. I want to get the angles on different sides because argument is basically the angle, right? So pi over 2 plus argument of z. Now, I have two angles. Let's call this angle alpha. And this is going to be pi over 2 minus alpha, right? Okay, great. So here's the thing. Now, or I guess I could call this alpha, and this will be pi over 2 plus alpha, and then this will basically be like beta, right? I mean the whole thing I can call beta, but beta is going to be pi over 2 plus alpha. Okay, makes sense? Now, what am I going to do with this? Here's the thing. Whenever you're given arguments, always checking the tangent is a good idea. For example, if you have z equals a plus bi, which is the name of this channel, right? Okay, I hope you know that. And from here, we can safely say that if argument of z is theta, and then tangent theta is going to be y, what am I saying? Not y, b over a, okay? Which is same as y over x, of course, in the xy world. Now, so given this information, can I just use inverse tangents? Like, can I say that theta is tan inverse or arctangent b over a? Well, yes, but you have to be careful because you have to pay attention to the quadrant in which this number resides. Okay, that's the only thing you need to pay attention to, because there are two angles whose tangent equals to the same number between 0 and 2 pi. That's why the period for tangent function is pi instead of 2 pi. Okay, I hope that makes sense. Draw a unit circle and hopefully you'll see what I mean. Now how can I use this information? Well, since I have the arguments, I can basically tan both sides, right? I can just tangent both sides, and hopefully that'll give me something helpful. Let's see how that works. So from here, I'm basically going to be getting tangent beta equals tangent pi over 2 plus alpha. What is alpha? I know it's argument of z. Okay, great. So let's go ahead and take a look at these values. First of all, what is tangent pi over 2 plus alpha? So that's something to know, that whenever you add pi over 2 or 3 pi over 2, or whenever you subtract them, you change the name of the function. Because think about it. You have an angle, let's say something like alpha, and you're adding 90 degrees to it, right? So notice that this triangle is flipped, right? So tangent and cotangent actually switch places. Makes sense? Okay, because you know what I'm talking about, hopefully. Okay, in other words, and if your angle is acute, and it's okay, safe to assume it's acute, because it's always going to work. When you move it to the second quadrant, the tangent is going to change sign. It's going to become negative. So in other words, this is equivalent to negative cotangent alpha. Awesome. Or I can write it as negative 1 over tangent alpha. So I got a really interesting relationship. Tangent beta equals negative 1 over tangent alpha. But what are those? Tangent beta and tangent alpha? Let's go ahead and find out. Beta is argument of z plus 2. Let's go ahead and write it down. And alpha is argument of z. And now we're going to replace z with, should we do x plus yi, even though the channel's name is a plus bi? It's okay. You get the idea. we're going to call this x plus yi, okay? And then we're going to get the following. Argument of x plus yi plus 2. So beta is equal to argument of, maybe I should do it here. Beta is equal to argument of x plus 2 plus yi, and alpha is the argument of x plus yi. And from here, I'm going to write the tangents, okay? Ready, set, go. All right, so now, how do you find the tangent of this number? Or in other words, tangent beta. It is actually this over that. Imaginary part divided by real part. So it's going to be y over x plus 2. Awesome. What about this? Negative 1 over tangent alpha. What is tangent alpha? Easy. Y over x, right? We talked about it. But if you flip it, that's going to become negative x over y. So now we're going to get our relationship. That's what we needed. With some caution, be careful. Now I'm going to go ahead and cross multiply. This is going to give me negative x squared minus 2x is equal to y squared. I should probably leave the negative at the bottom, but anyways, let's put everything on the right hand side. X squared plus 2x plus y squared is equal to 0. Awesome. Is that the answer? No, we got to work it out a little bit. Okay, so now notice that I can add 1 to both sides to make this a perfect square. And that'll be perfect because that's going to give me the equation of a circle, isn't it? Yes. A circle with center at negative 1 comma 0 and radius 1. Awesome. I can graph it, right? It's going to look like this. And don't worry, I'm going to give you a much cleaner version of this circle. But for now, bear with me. And we can basically talk about a circle that looks like this, please. Yes, awesome. It worked, finally. Okay, so that is the circle I'm looking for, right? Pretty much. Okay, great. So, well, it's not so great, but let's go ahead and pick a number. So in other words, any point on this circle should satisfy our original equation, right? So let's go ahead and pick a sample. How about negative 1 plus I? If z is on the circle, which is negative 1 plus I, it should satisfy my equation, wouldn't it? Let's go ahead and find out. What is z plus 2? Add 2, you're going to get 1 plus I. Just z is going to be negative 1 minus I. And then we're going to multiply by the conjugates. That's going to be 1 plus I, 1 plus I. And here I'm going to be getting 1 plus I squared, which is 2I. And then from here I'm going to be getting 1 plus 1, which is 2, but that's a negative 2. And I'm going to be getting the argument of negative I. Uh-oh, the argument of negative I is not pi. It's actually negative. I mean, it's not pi over 2. It is negative pi over 2 or 3 pi over 2. Make sense? Why didn't it work? Because locus problems are just like that. Especially with circles, you have to be careful. You have to check your work. That's why the second method is awesome. I can show you how to check with the first, but that's going to be redundant. So here's what we're going to do. Again, we're going to do the same thing pretty much. So we're going to replace z with x plus yi. Let's do it. And then we're going to get argument of x plus 2 plus yi over x plus yi equals pi over 2. But let's go ahead and rationalize the denominator. I mean, did I say rationalize? I'm sorry. Let's go ahead and multiply by the conjugates to do the thing. And that's going to give us the pi over 2 again. But if you simplify this, you're going to do the following. Multiply the real by real. Then you're going to get argument of x squared plus 2x. And then multiply the imaginary by imaginary. That's going to give you negative y squared I squared, which is plus y squared. Uh-oh, the same thing pops up again. And then multiply the real by the imaginary and the imaginary by the real. That's going to give you xy minus xy minus 2y, all multiplied by I. And all of that is divided by, what do you get? Remember the sum of two squares you get from multiplying conjugates. Awesome. A lot of work, but it's definitely worth it. Now, we're going to go ahead and separate this into real parts and imaginary parts. So our number can be written in standard form. So we're going to get x squared plus 2x plus y squared divided by x squared plus y squared plus xy is going to cancel out. Yay. We could probably put a minus sign here to make it easier. Or plus minus is okay. 2y times I. What is that supposed to mean, right? Well, we kind of got the same idea, because if the argument of something is pi over 2, that means it's on the positive, can you say positive imaginary axis? You get the idea. The positive y-axis or the imaginary. So it's supposed to have a real part of 0 because it's purely imaginary. So this is supposed to be 0. Yes. And that gives us the exact same circle that we found before which was, remember, x plus 1 squared plus y squared equals 1, and that is the circle we talked about. You'll see a graph of it in a little bit. But we have an additional condition which doesn't show up with the first method, and the imaginary part needs to be positive. Yes, that's the correct statement. This is supposed to be greater than 0. So negative 2y must be positive. What is that supposed to mean? It means y must be negative. So you have the circle, but y must be negative, which means that you're only going to be looking at the half of the circle, which is the bottom half. And this brings us to the end of today. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.